We're ready? All right.
Okay, well, I should introduce Jonathan. Well, thanks for coming to our last seminar of the year, I think. Yep. And I'm pleased to have a guest speaker who is a postdoc working with me, Jonathon Schuh, who got his PhD in mechanical engineering about a year ago.
Yep.
And we needed somebody here to teach 330 and to continue the G&W electric actuator modeling and control. And nothing like a mechanical engineer to help out in an electrical engineering job. So he knew more about what he was doing than I did. So thanks for coming, Jonathan, and go ahead.
Thanks for having me. All right, so we'll go ahead and get started. So today I'm going to be talking about this thing that we're trying to do with towards sensorless control. So the reason it's towards is we haven't fully implemented it yet, but we are talking about the modeling and stuff that we're doing, and this is for a permanent magnetic actuator. So let's talk about these actuators a little bit. So magnetic actuators have gained use in control applications mainly due to their reliability and efficiency. So they've been being used a lot in these control applications. And our particular application that we want to use this for is we're looking at using this as a circuit breaker, okay? So we want this actuator to act as a circuit breaker for the energy grid. And so what that means is we want this actuator to be able to close at a zero crossing. So we don't get these big arcs when these things open or close. And in order to do that, we're going to need a very accurate prediction and control of the closing time in order to hit that zero crossing. All right. So that's what we're trying to do. So currently, the actuator, it looks like this. Okay. We have a linear potentiometer that's attached right here, and this is the top of the moving plunger on the actuator. So as it moves, we have the linear potentiometer that feeds back the position measurement for us, all right? And so that's currently how this thing is set up. There's a problem, though, in that this potentiometer is likely to fail before the actuator itself. And so that leads to increased maintenance for this, which is what G&W doesn't want. They're our corporate sponsor on this, so they want to decrease the amount of maintenance that you need on these actuators. And so we want a way to remove this potentiometer, but still get that position measurement in here. And so what we're going to do is we chose to estimate the position of this actuator from the current measurement. All right, so that's we just attach a little current probe to the wires that are coming out that are supplying energy to the actuator, and from that current measurement, we're able to estimate the position. And so that's what we've chose to do. And so going forward, I'm going to talk about this. All right, so I'm going to talk about the model that we're using that's relating the magnetic field and the position and the electric field. I'll talk about how we validated this model against experiments, and then how we use this model for predicting our closing time. And then at the very end, we have some preliminary results where we're using this for controlling to try and hit that zero crossing. So that's my outline for today's talk. So just to show you what we're talking about with this actuator before we do anything, these are two videos that are showing the actuator opening and closing. Now, we have both of them on here. We're mainly concerned with the closing rather than the opening, but we have both of these videos here, okay? So here's a picture of the actuator opening. Okay, that's really weird. It flipped on us. But basically what we do is when we apply the voltage to it, it opens up. And then we also have this video of it closing. Again, I don't know why it's flipped over like that, but when we apply the current to it, and it rises back up. So that's the closing and opening of this actuator without adding any control schemes or anything into it. That's just how it behaves on its own. All right. So now we know how it behaves, so let's do this electrical modeling. So we're using some Maxwell's equations, as I've written them up here, and we're using integral form because that's easier for us. And we have these written up in this way. So HM is the magnetic field of the permanent magnet that we have up here. HW is going to be the magnetic field inside this little air gap. And then HY is the magnetic field in this big air gap that we have down here. And V is the voltage that we're supplying, I is the current, and all of that's following through. Now, one of the things that we are going to do here is we have that magnetic field from the permanent magnet. And so what we're going to do is we're going to assume that the permanent magnet is on its demagnetization curve. And what that's going to do is it's going to give us a nice relationship between the B field and the H field, because we need this H field to plug back in here. And so this is the equations that you get relating the B field and the H field in here, where M is the remanence magnetization of the permanent magnet. All right, so that's what that M is. And so what you can do is you can take that, you can plug it into this equation up here, you can simplify things down, and you'll eventually get something that looks like this. Okay, what's going on? Okay. No, I don't think I did. All right. There we go. I got this. Oh, great. Okay. Yeah, all of those are redacted apparently. Yeah. No, what happened, I think, is so I made this PowerPoint on a Mac, and we converted from a Mac to PC, and I guess those two don't like talking to each other too much. So I guess that was the problem that was going on. So hopefully we can try. It says repaired, but it doesn't have anything in it. Okay. I have the original PowerPoint on here. We can try that. If not, I guess this will just turn into a little bit of a chalk talk if we need to.
So I clicked on this top one. Was there something, another version of this?
No, it's just that top one. That's the first one. Yeah.
If you want to, you can just go PDF it on your computer, and we can have a 2-minute discussion about the voting.
Okay.
If it looks like it's still showing.
All right, I'll go save it as a PDF copy really quickly, and then we can just go through with that. And then I'll just have to bring in I had some videos that I was showing, so I can just copy those videos over. I wanted to show, so I would just copy those videos over as well. So when we get to those parts in the PowerPoint, we might just skip them and then go back to the videos later, or we'll get you to see those videos somehow. Okay. All right. So are you ready, Kevin?
Yeah. Do you have control?
Yes, I do. All right. So we finished up talking about the electrical model, all the things that we added into it. And so if you go through and you simplify things down, you'll eventually get this term right here for the flux linkage, where IM is going to be a term that's going to be from the permanent magnet. We can rewrite things in terms of a current with the permanent magnet. And so we get things that look like this, where L0 is the inductance when Y of t is equal to 0, and LL is the inductance when Y is equal to the maximum extension Y. And you can see that it works out like that here. So if we take that and plug this into this equation for the voltage, we get this expression, which should look very similar to things from ECE 330. So all we need to do to complete this model is we need to know what is L0, what is LL, what is the resistance, and what is IM. And once we know all of those values, we can complete this model for the circuit part of it. All right. And there's a note that we're going to talk about here about eddy currents. So the outer casing of the actuator right here, we believe it's a solid piece of metal. We don't think there's any laminations or anything in that. And so because of that, eddy currents could be important being developed inside this outer casing. And so we found a paper where you can get the eddy currents, you can approximate their effects using this term right here, this 1 minus e to the t over tau, where tau is just some decay rate for the eddy current effects on the magnetic field. And so that's what we've chosen to do here, is just include that as our approximation for these eddy current effects to the full magnetic field. So we're going to be using that going forward in our model. Okay, so now let's talk about how we're going to determine L0, LL, and R. Okay, so these are the parameters for the inductance and the resistance. And so we know that before and after closing, so when this thing, before it has started to close, that's fully open, and it should behave like an RLC circuit, a simple RLC circuit at that point. Same thing when it's fully closed. It should also behave like a simple RLC circuit, so we can solve what those things are at each of those two extremes, and we can fit those expressions to the experimental data that we've got in these two regions, where this is right before it started to move and right after it has completely closed. And so what we did is we did the fitting to each of these things in Python. We did a simultaneous fitting where we fit this region and this region at the same time. And we did that using Python's built-in nonlinear fitting function. We didn't use any weightings on the residual. And for this, I just fixed this value of L naught. It seemed to work pretty well for what we needed. And so from fixing this value for L naught in the fitting, we got these two values for the resistance and the inductance when this thing is fully opened. Okay, so those were the two values that we have for our system, and that's what we're going to be using going forward as well. So some comments on these model parameters before we go on. So one of the things with the inductance is as this actuator is being charged, okay, we have the current flowing through, we could have a change in temperature. Also, this is going to be sitting out in the field, and so you could have extremes in temperature as it's being operated. And so what we have gone through here is we've just gone through a simple analysis to see how do these inductances change as the temperature is changing. And you can show after you go through and write all these things out that you get these two expressions for the inductances as a function of temperature, where alpha m here is the coefficient of thermal expansion for the permanent magnet. You can write things in terms of that. And so you have this term that shows up in here. And for the permanent magnet, the coefficient of thermal expansion is on the order of 10 to the minus 5 per Kelvin. Okay, just looking up what those values might be. And so if you go through, you would see that to get a 1% change in these model parameters, you'd need about a 1,000 degree Celsius change in the temperature. So for the most part, we can treat L naught and LL as constants. We're not going to be seeing that wide range of temperature change in order to get a 1% change in the model parameters. So we can keep these things as constant going forward. But what about the resistance? The resistance is going to be a little bit different. Again, as this thing heats up, the resistance can change, and that can be really important for our model. And so you can write the resistance as a function of temperature using this as our initial starting point. And here alpha is going to be the change to resistivity as a function of temperature. And we've written down copper and aluminum. We're not sure what wiring is actually being used in this, whether it's copper or aluminum. So we just use both of these two parameters in there to get an estimate of what the temperature change would have to be to get a 1% change in the resistance. And for this one, we now see that it's a 2 degrees Celsius change. So just a 2 degrees Celsius change in the temperature can give you a 1% change in the resistance. And that can be really important as you're going through with this. So you need a really accurate model for the resistance in order to have this model to be working. So you just need to keep that in mind going forward. So that's all the electrical side of things. But this electrical side is being used to make the actuator move. And so that's where we get into the mechanics. All right, so now let's talk about our mechanical model. What I've shown right here is a free body diagram of the actuator plunger. We have these 4 forces down here that are acting on the plunger. We have a spring force. We have the force of electric origin. We have the weight of the actuator plunger. We also can have a drag force in there as well. And then if you want to, you can also include some frictional force as the thing is sliding. That can all be included in there. And so when you go through and do Newton's second law, you get this equation right here where you have mass times acceleration is equal to the sum of the forces acting in the positive y direction, which we've defined as down. And then you also have this velocity equation right here that's just a true statement. So we need these constitutive relations for these forces in order to actually solve this and figure out what the position is going to be. So let's talk about those constitutive equations. First is the force of electric origin. This is probably the one that's most familiar to you from ECE 330, where we're getting the force of electric origin from the partial derivative of the co-energy with respect to y, where we're calculating the co-energy using this equation right here. And you'll notice that we're integrating from minus Im up to I rather than from 0 up to I. And that's because we need the current to equal minus Im for this thing to be completely off. We're not going to get any motion in there. So that's why just a little note on that when you're doing this integration. And when you go through and do that and simplify everything out, you get this expression for what the force of electric origin is as a function of time, because we still have these eddy current effects that are showing up in here, so we need to include that. And then we have this term here that's I squared, which should be very familiar with from the ECU 330. All right. So that is our force of electric origin. So now let's talk about the spring force and the drag force, because these things might be a little bit new. So we're going to assume that we have a linear spring in here, so we can write the spring force as a restoring force. That's why we have this negative sign in here. It's trying to restore everything back to equilibrium. So that's why we write it as this. So K is our spring constant, Y equilibrium is just the equilibrium position, and we can calculate that equilibrium position from this expression right here by plugging in when y is equal to 0. So we can measure at those two places, and we've done that, and so we can calculate the spring constant and the equilibrium position, and we can plug that in. The other thing that we need to do is this drag force. Now, this, when the plunger is moving, all right, so when the plunger is moving, you have air that can be caught between the top of the actuator and the plunger itself, and that actually creates a little bit of a squeeze film, fluid film, that shows up in there, and so that actually causes the drag term to increase as this thing gets smaller and smaller, but then eventually you have the fluid that starts to flow out, and so the drag force can go down a little bit. So this is how we're approximating the drag term for the force right here. Okay, you can see I have this minus C naught. Again, this minus sign is because it's opposing the velocity, it's trying to slow it down. So that's why we have this minus sign, and then we have these two regions when we're applying these two different terms for the drag force. All right, and that's just from playing around with this compared to the experimental data to find where that region is where we've had enough air start to squeeze out that the drag force can go down. All right. So we've talked about the force of electric origin, the spring, and the drag force. The weight's real easy. It's just mass times gravity. That's the easiest one to throw in here. So let's talk about the friction force. All right. So from the experiments, we've seen that there's really no movement in the actuator until about a current of 15, a little bit bigger than 15 amps. All right. So what we're going to include is we're going to include this frictional force to help us reach that point. Okay, so that there's no movement in the actuator until we have a force exceeding this friction force, and we can calculate that using this equation where we're assuming the eddy current effects have died away at this point, and so we can just calculate this frictional force. And this is going to be applicable right before the actuator starts moving. And then once it starts moving, the friction force is gone. So this is just a static frictional force. It's holding it in place at the very bottom. Once it starts moving, the frictional force is gone. That's how we're including it in our model right here. So now we've talked about all of these forces in here. We've talked about the inductance terms in our inductance equation, and we've also talked about the resistance, but we haven't yet talked about IM. We need to figure out what that IM is in order to complete the model. And so that's what we have right here. Okay, this is how we're going to determine IM. We know that when the actuator is fully closed and there's no current, there's no motion, and we can neglect friction, that the force of electric origin must balance the spring force and the weight when this thing is fully closed. Okay? It's not moving, so those forces have to be balanced. And so when you go through and do that force balance, you get this expression for what IM is. You could get a negative term as well, but we're only choosing to use the positive term here because of the square root. But when you go through and do that, that's going to give you an expression for what, IM is going to be equal to. So now we have completed our model. We've gotten everything that we need. Now we can actually start writing out these governing equations. All right, so here's our full set of governing equations. Our voltage is coming from a capacitor, so we have this equation for how the voltage on the capacitor decays as we're drawing more current from it. This is rearranging the voltage equation to get the change in current as a function of time. This is Newton's second law, and this is the velocity function. All right. So again, with this, in order to do this completely, you need to have this really accurate model for what the resistance is as a function of temperature. But what we're going to be doing is we're going to be measuring the current, right? That's what we want to do. We want to measure the current and get position from it. So if you do that, if you measure the current, you only need these two equations, Newton's second law and this velocity term right here. And so what that does is it eliminates the need to have that really accurate model of the resistance as a function of temperature. That's included in the current that you're measuring. So you don't have to include it in your model anymore. And so that's really nice. We can eliminate this need for that resistance as a function of temperature equation. All right. So we've gotten our model, we've plugged everything in. Now let's do some model validation. So what we've done is we've run some experiments with the help of Yu Yao and Leslie, and we've run some experiments on this actuator. And so what we're going to be showing right here, this is a video, so we'll go back and talk about this video in a second. But what we've done is we compared the experiments Okay, we can get a closing time in the experiments, and we can compare that to the closing time from our model, and we can see really good agreement between these two. Okay, so the model is doing a very good job of approximating what's going on inside the actual actuator. And this is from data taken back in November of last year. All right, we did the same thing about a week ago, 2 weeks ago, I think at this point. We did the same thing, all right? We took the same model. We didn't change any of the parameters. We tested the actuator again. And you can see we're still getting some pretty good agreement between the experimental closing time and the model predicted closing time, all right? So this model is doing pretty well. So we validated it at least for what we want it to do, all right? So now that we've validated the model, we're going to go through to estimating the closing time. This is the thing that we really want, okay? We want to have this accurate representation of the closing time in order to do our control. So what we're going to do is we're going to use position and velocity data at each time step, and we're going to do a linear extrapolation to approximate the closing time. Basically what we're doing is we're saying that here's where I'm currently at. I want to get to position 0 in the way that we've defined things. We have our current velocity, and we have the time. And so TA is the approximate closing time. That's the thing I want to get. And when you go through and you can rearrange it, you get this expression for the approximate closing time, depending on where you are right now, and this relationship between the velocity and the position. And this should look somewhat familiar. This is like a first step in a Newton's method for approximating a zero crossing. So as we get closer and closer to the actual closing time, we get a better and better approximation of what the closing time of the actuator is, and that's really nice. And so all this video is showing is how we go through and do that. I forgot to copy that video over, but it's basically saying we want to get to the 1 up here, and so we're approximating the time it's going to get there, and you can see as we get closer and closer to that, we get a better and better approximation of the time in order to reach that. So that's how we're going to be estimating closing time. And that is being used in this block diagram, because again, we want to be using our control. So what we have here is we have some desired closing time. This corresponds to a zero crossing of the 60 hertz sine wave. And we're going to be putting that through a PID controller, and that's going to be controlling the voltage duty cycle, because we have an H bridge in here that's controlling the voltage to the actuator. And so we can control the duty cycle on that to open and close the H bridge. And that's going to our plant, that's the actuator. And so we're getting an actual closing time out of that. But we're not measuring that in any way, all right? We don't know what that is. What we do know is we know the current. And we can get that current measurement, and we're putting it through this estimator right here. This is the model that we've talked about. And once we have that estimator, we get our estimated closing time, and that's what we're using as the error that's being fed into the PID controller. So it's kind of like an indirect control scheme that we're using right here, all right? And we're estimating, we're going to be controlling the duty cycle using this expression for the PID controller, okay? So Kp is the proportional gain, Kd is the derivative gain, and Ki is the integral gain, where we're doing this estimating the error as the difference between the desired closing time and the estimated closing time we get from the model. All right.
Do you have what's inside the estimator?
We do have it. It's written down. It's all of the stuff previously that we did. It's all the model and estimating the position and velocity and all of that. So yeah, we have that estimator. I can update the presentation if you'd like to make that a little bit more clear. Okay.
Mysterious box right now.
Yeah, right now it's the mysterious box, but it's the model that we've talked about. So this is a video where we're trying to simulate, okay, we're doing a simulated version of the plant because we haven't done this on the actual actuator yet. Okay, so this is just a full simulation. So if I go back here, my plant is a simulated version of what's going on. It's those 4 differential equations that we're using, and we're controlling the voltage duty cycle into this. And so what this video showed is this is my actual position. Here's the predicted one. I've got this video we'll show you in a little bit. And what we're doing is here is the voltage that we're supplying to the actuator, and you can see the duty cycle is changing as we're measuring or estimating the position of the actuator as it's closing. And we're trying to hit a zero crossing right here. Okay, this corresponds to a zero crossing. That's the closing time that we want to hit. I've got that video. I'll show you that in a second. This video, what this is showing is, again, we have this 60 hertz sine wave, and it's oscillating back and forth. And we're trying to hit a zero crossing right in here. And so what this is showing is how we're hitting that zero crossing. This is the actuator closing, and this is just a schematic of that actuator closing. And then again, we have our predicted values in red and the actual ones in black, and I'll show you that video in a second. So that is what we've done up till this point. What we've done is we've developed a model for estimating the position of the actuator using a current sensor. We're using this current feedback, and it eliminates the need for including the resistance as a function of temperature, because that's just included in the current already. We've found that eddy currents are important, and you can use these eddy currents as a design variable, so you can change what this material is made of. If you want these eddy currents to be longer or smaller, you can include that as a design parameter. And the simulations, I'll show you this video so you can actually see it. But we can with this control scheme, theoretically, we can get it down to less than 0.1 degrees in phase difference between trying to hit that zero crossing and where we're actually closing at. So we can hit that pretty nicely. So some of the future work that we're doing on this is we're implementing this on the Arduino to control the actuator in the lab. We've done some preliminary data for this, but one of the problems is that I was copying some code over and I forgot to change the something in the code in 2 parts. I only changed it in 1, and so we're getting some weird results. I have corrected that now, so we can actually go through and actually test that. But this is some preliminary data where if you just make the controller have to be active, instead of using the friction force, you just make the controller have to be active. You can see that we are changing this duty cycle in the actual experiments. This is all actual experimental data that we've collected. So you can see we're changing the duty cycle on the voltage, and you can see that when this duty cycle drops down to 0, when the voltage drops down to 0, you can see a decay in the current as to be expected, and then when the voltage is active again, you can see this rise. And this is all corresponding to delaying this closing of the actuator. And so we can move this to a closing time of about 130 milliseconds that we're seeing right here, compared to the 100 milliseconds that we got for just always applying the voltage. So by using this, we can delay that closing time. And so we should be able to hit that closing time that we want to achieve. And so we need to actually do that now that I've corrected the model. And so that's the next step, is actually testing this again. So at this time, I'd like to acknowledge some people. I'd like to acknowledge my supervisor, Pete Sauer, Karuba Haran, who's been helpful on this project as well, G&W, who's our sponsor for this project, and then the graduate students, Nate Renner, who worked on this project before I got here, and then Leslie and Yuyao, who helped with the experimental data. And there's my contact information. We're going to be trying to send this off to G&W at some point, so I wanted them to have my contact information as well. And so I'd be happy to take your questions at this time, and I will also make sure to show you those videos.
Nate was here for the picnic. I guess he's gone now.
All right, well, you guys are thinking of questions. I'll go ahead and get those videos up and running.
I can drag them over here and see if they show up in these MP4s.
Yeah, those MP4s are what we want.
Let's see if we can bring it up here.
Adobe Acrobat could not open. Oh, I think it's because we're opening it in Adobe. So what happens if we just double click on it? There we go.
It's still loading or whatever. Is that
There we go.
was that it?
No, that wasn't it. We're just having. Yeah, I'll try it. We'll try it and see again. We're just having some computer problems. I'm sorry about that. There we go. All right. So this is some of the experimental data. So again, we have the red. That's our model. The current is what we're measuring, okay? We're reading that in. And the black is the experimental values. The red is the prediction. So I'll go ahead and show you that again so you can see that we're actually getting some pretty good agreement between the model and what we're actually measuring on the actuator. So this is pretty good. This is the data that we collected about 2 weeks ago. Let's go back over here. Here's the data from back in... Yeah, this is the one back in November. All right. So again, we're seeing very good agreement between the experiments and the model with both of these. So that was the validation of this model. Here is, this should be one of the control schemes. If I can get that up and running. Okay. Yeah, this is a little bit bigger of a video, so it might take a little bit longer for it to load up. Okay, yeah, we'll show this one. So this is where we're trying to hit the zero crossing on the sine wave. So you can see as we're going through in time, the voltage is oscillating as a function of time, and so we start moving. We're trying to hit this zero crossing, and you can see the actuator starts to move, and then boom, we hit that zero crossing that we're trying to hit. Okay, so that is what that video was showing, is trying to hit that zero crossing on the voltage sine wave. So those are all the videos that I had. Yeah.
So obviously, if you're trying to close the breaker,
Mm-hmm.
when you get within a certain range, you can have arcing.
Mm-hmm.
How far, like how quickly do you have to close that last incremental distance from that arcing? Have they commented on that?
No.
Does that my question make sense?
Yes, your question does make sense.
You're closing over 100 milliseconds, but your line cycle is like 60 milliseconds. So like,
Mm-hmm.
how fast do you have to close that last little bit so you don't arc?
That's a very good question. I honestly don't know. I haven't looked into
I
that.
don't know anything about arcing.
Yeah.
You need a high voltage person for that. I don't know.
It's even on the reverse case, when you're trying to open, how do you know that you have enough force to really open and not get caught?
Yeah, that's a good question as well. We haven't looked at that. We really aren't really concerned that much with the opening at this point. We've really just been focusing on what's going on in the closing. They're more concerned with that at this point. But yeah, that's something that we could look at. We just haven't looked at it yet. Yeah.
You know what voltage ratings they intend to use this for?
72 kV.
Okay.
Mid voltage.
Mm-hmm. All right. Thanks.
GMW is looking to hire people too. So.
Thanks, Kevin.